Welcome to Variational Principles and Lagrange's equations. Today we are going to discuss conservation theorems and symmetry properties. A system having n degrees of freedom will obey n differential equations of motion that are of second order in time and thus require 2 times n integration constants, which are the initial conditions qj and their derivatives with respect to time. So the initial conditions are the values of the generalized coordinates and respectively the values of the generalized velocities at the initial time. Even though most problems cannot be fully integrated, a lot of information can still be gained regarding the physical nature of the system's motion. This can be more important than the complete solution of the generalized coordinates as functions of time. The quantities f, depending on generalized coordinates, generalized velocities, and through them on time, which obey the condition that they are constant throughout the motion, are called first integrals, or in other words, the conservation laws that have been studied previously. For a system of particles moving in a position-dependent potential, it is clear that the derivatives of the Lagrangian with respect to velocities will only contain the velocity-dependent terms in the kinetic energy, and by definition, this quantity, for example, for the derivative with respect to the x component of the velocity for particle I, is just the x component of the linear momentum of particle I. Now, in general, we are going to define by p index j the partial derivative of a Lagrangian with respect to the generalized velocity qj. And this is the canonical or conjugate momentum to the coordinate qj. This momentum needn't necessarily correspond to the linear momentum, and for velocity-dependent potentials, it needn't even correspond to mechanical momentum. For example, in the case of charges moving in an electromagnetic field, we have established previously that the Lagrangian has the expression here, so involving the kinetic term, a potential term involving the scalar electromagnetic potential, and a second potential term involving the vector electromagnetic potential. And then in this case, if we apply the definition here and, for example, wish to calculate the x component of the canonical momentum of particle I, then it follows immediately by taking the derivative that this canonical momentum contains both the linear momentum of the particle and an additional term, which is the one here involving the x component of the electromagnetic vector potential. If the coordinate qj is not contained within the Lagrangian, it is known as a cyclic or ignorable coordinate. And in that case, if we write the Lagrange equation for the qj generalized coordinate in its general form, and we apply the condition that qj is not contained within the Lagrangian, then this derivative vanishes, and it follows that the equation reduces to the form here, where by definition the derivative in the bracket is just the j component of the canonical momentum, and therefore what this equation says is that the j component of the canonical momentum is constant. So the generalized momentum conjugate to a cyclic coordinate is conserved, assuming qj is linearly independent of all other coordinates. Care must be taken with constraints, as coordinates absent from the Lagrangian can be contained within the equations of constraint, and as such they are not cyclic, as was the case of the problem of the rolling hoop, where the angle of rotation phi was implied in the constraint of rolling without slipping. The result 246 is a first integral of the type of equation 243 and is a more general case of the momentum conservation law previously derived, as it also applies to electrodynamics where the law of action and reaction is violated. So what this result says is that, for example, Px being equal with the sum here is a constant if the coordinate x is not contained in the Lagrangian. In this case, the mechanical momentum is not conserved, but rather its sum with q times a index x is the conserved quantity. In this particular case, the additional term is precisely the x component of the electromagnetic linear momentum of the field associated with the charge q. However, the result 246 should still reduce to the previous mechanical results given proper restrictions. Consider, for example, a coordinate qj with dqj being the infinitesimal translation of a system as a whole in a given direction, as for example one of the Cartesian coordinates of the system's center of mass. As velocities are not affected by a shift of the origin, then the partial derivative of the kinetic energy with respect to qj is 0. And we are also assuming that the partial derivative of the potential with respect to the generalized velocity associated with qj is 0. So the potential is dependent only on coordinates. Then if we write the Lagrange equation down, then this is equivalent with the first term involving only the derivative of t, while the second one involves only the derivative of v. And as such, what we obtain immediately is that the left-hand side is just the derivative with respect to time of the canonical momentum Pj, while the right-hand side is simply the j component of the generalized force q. Now, we know that by definition this component is equal with a sum over all the particles in the system over the dot product between the force applied to particle I and the partial derivative here. So the partial derivative of the particle I's radius vector with respect to the generalized coordinate qj. And we can express this derivative just by using the standard definition, using the limit. So it's a limit when dqj goes to 0 out of this ratio, the infinitesimal difference of the two vectors divided by the infinitesimal displacement. But if we're speaking about a translation, then clearly the difference here is just a vector pointing in the direction of translation and having as magnitude precisely the value dqj. So obviously these simplify, and the derivative is simply equal to the versor giving the direction of translation. And thus qj is simply the dot product here. So it's the component of f in the direction in which the system is being moved. Then we know the definition of the kinetic energy, and from this we can immediately calculate the canonical momentum as given by the expression here. And then if we use equation 151, then we can express the derivative here as the result here. And then if we make use of result 249, which gives us the value of this derivative in terms of the versor, it follows that Pj is given by the dot product of the total linear momentum of the system and the direction in which the system is moving. For position-dependent potentials, if Qj is cyclic, then the potential is independent of the generalized coordinate in question, and as such the j component of the generalized force is 0. And it follows that the corresponding component of the total linear momentum is conserved. In the more general case, however, we could have a situation where the Lagrangian contains a kinetic energy term and the generalized potential term, which depends both on coordinates and velocities. And in this case, the Lagrange equation is in fact given by the explicit result here. So the first derivative contains, the first term contains both the derivatives of t and u with respect to the generalized velocity, and this is just the canonical momentum in this more general case. And as such, what the equation says is that this its derivative with respect to time, the derivative of the canonical momentum, is equal with minus the partial derivative of u with respect to qj. Now we've already established the first result here, and as for the so this one regarding the derivative of t with respect to the generalized velocity, but if we look at the derivative of u, then by using the chain rule of differentiation, we can write the expression here, and we've already used the result of equation 151 relating these two quantities, and then for equation 249 we know that this quantity is given with is equal with the versor here, so the whole result is just the expression here. It's the dot product between this versor and the sum over particles of the gradients of u with respect to each particle's velocity, and as such the result is that the canonical momentum p conjugate to the generalized coordinate qj is equal with the expression here. So the first term is just the component of the linear momentum in the of the mechanical momentum in the direction of translation. So mechanical or linear mechanical momentum, it's the same thing. But we also have an additional term which involves a dot product between the direction of translation and the gradients of u with respect to each particle's velocity. In the case of the electromagnetic field, the generalized potential has the expression here, so it follows immediately if we consider the value of the gradient with respect to velocities for this potential, that the particular expression of the canonical momentum contains a sum of two terms. One of them is the projection of the linear mechanical momentum on the direction in which the system is moving, and the other one is the projection of the field's electromagnetic momentum on the same direction. Now, in the case of a conservative potential V, we can let dqj denote an infinitesimal rotation of the system of particles about a given axis. Then the first equation is still, the first result is still generally valid. The second one is the definition of the generalized force, specifically its component j. And then the magnitude of the change in the radius vector of a given particle is simply this is the normal component of the vector on the axis of rotation multiplied by the angle of rotation, which is simply dqj. And as such, the magnitude of this partial derivative is just the normal component of the vector on the axis of rotation, and then the derivative itself is just the cross product between the direction of rotation and the radius vector of the particle that is being rotated. And then so we take this result back in the definition of the generalized force to get the expression here, and then we use the definition of the cross product in terms of the Levi-Civita symbol, where I'm using the summation convention for the double indices included in the symbol. And all I've done here is simply do a double permutation of the indices, which preserves the sign of the cross product. And what this amounts to is essentially a cyclic permutation of the vectors here into obtaining the result given here. So the conclusion being that Qj is the dot product between the direction of rotation and the sum over particles of these cross products, which are just the torques applied to each particle, and such that their sum is the total torque that is being applied to the system. We know the definition of the canonical momentum Pj as being the one given here, and we've just calculated that this derivative is given by the expression here, and by using the same technique that was illustrated above, we can perform a permutation of the vectors and this mixed product to obtain the result here, which is just the dot product between the direction of rotation and the orbital angular momentum of the system. So if Qj is cyclic, the corresponding component of the total orbital angular momentum for rotation about the direction of versor En, let's say, is conserved. Now for the case of a generalized potential in the electromagnetic field, this is the kinetic energy, and the partial derivative of the kinetic energy with respect to the generalized velocity Qj. And we know the derivative here is given by this expression, so this partial derivative is just the dot product between En and the orbital angular momentum. And then if we look at the partial derivative of u with respect to the generalized velocity Qj, we once again apply the chain rule of differentiation. So we have a sum of all particles and the partial derivatives of u with respect to the velocity of each particle and a dot product with these partial derivatives. But we already know this from equation 151, and we also know that this is equal to what we have obtained here. And then once again, by doing a simple permutation of the vectors in the mixed product, we obtain the result here. So in the general case, the canonical momentum Pj of a system moving in a velocity-dependent potential has the expression here. So it contains both in the case of rotation specifically, it contains both an orbital angular momentum and this more general term, which in the particular case of the electromagnetic field becomes the expression here. So we have a mechanical orbital angular momentum and a kind of angular momentum which belongs to the electromagnetic field itself. In conclusion, momentum conservation theorems are closely connected to symmetry properties. Consider a particle moving without dissipation in a conservative force field produced by various mass distributions, such that the force is always proportional to a volume element of the distribution and the scalar distance between it and the particle. Then in the case of a distribution that is uniform in the z equals 0 plane, the conserved quantities are the ones listed here. So we can move in the x or y direction, or we can rotate around the z-axis and preserve symmetry, but we cannot move in the z direction or rotate about the x and y directions without breaking symmetry. In the case of a uniform distribution in the half plane given by z equals 0 and y greater than 0, we can only preserve symmetry by moving in the x direction. If we were to move in the y or z directions, we would break symmetry, as would be the case if we tried to rotate about any given axis. Now, in the case of an infinite circular cylinder, then we can, assuming that the cylinder is orientated in the z direction, we can move parallel to the cylinder, and we can rotate about the symmetry axis of the cylinder, but obviously we would be breaking symmetry if we try to move in any other way. If the cylinder happens to be finite, then we cannot even translate on a line parallel with its symmetry axis without breaking symmetry. All we can do is rotate about that axis. If the cylinder is infinite, but it happens to be elliptical in nature, then we can only translate about its symmetry axis, as all other symmetries are broken, particularly the rotational symmetry about the cylinder's axis of symmetry. And if the distribution is given in the form of a dumbbell, then we can only rotate about the dumbbell's axis of symmetry, as any kind of translation or the other two axes of rotation would break symmetry. And in the case of a uniform distribution in an infinite helical solenoid, then we have a more complex preserved symmetry, which involves both translation along the solenoid symmetry axis and rotation about it, with the parameter a being given by the step of the helix. So anything else would break symmetry. In conclusion, in this section we have defined the concepts of first integrals and cyclic coordinates. We have discussed the connection between conservation theorems and symmetry properties. Emphasis was placed on momentum conservation for conservative, generalized, and electromagnetic potentials, both for translations and rotations. In the following, we will discuss the energy function and the conservation of energy. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.